And let's finish off Chapter 6 by discussing orthogonal matrices and orthonormal bases. To get to these concepts, I am going to take a back road through the country to enjoy the geometric scenery. If you are lucky enough to have had a decent course in geometry, you might be familiar with the notion of an isometry, which is a transformation of a space that preserves distances between points. Let's consider an example or three. A translation is an example of an isometry, because all we do in a translation is to take each and every point in the space we are transforming and displace those points by moving them in a fixed distance and direction. Such a simple transformation clearly preserves distances between points. Here, for example, in my original figure, the distance between the smiley face's open eye and this point on the letter R, that distance right there, is preserved in the image, that distance right here. Those distances are the same because a translation is a distance-preserving transformation. It is therefore an example of an isometry. Note, however, that although it is an isometry, a translation is not a linear map. It's not a linear map because a translation would move the origin. It moves every point, and we know that linear maps always preserve the origin. So, how about an example of a linear isometry? Well, a rotation about the origin would be a simple example in R2. If we begin with some stuff in R2, again, my smiley face and the letter R, and we rotate everything through some fixed angle about the origin, then the positions of individual points change, but the positions of points relative to one another does not change. Any distance we look at on our original picture is going to be preserved on our rotated image. Rotating a space, whether we are rotating a two-dimensional space around a point, or a three-dimensional space around a line, or a four-dimensional space around a plane for that matter, or so on in higher dimensional spaces, is an example of what a physicist would call a rigid motion, meaning that there are no distortions involved. But we in the mathematical world would call it an isometry, because a rotation preserves distances between points. Whatever a certain distance was before the rotation occurs, it will be the exact same after the rotation occurs. And if we are rotating about the origin, then this isn't merely an isometry, it is now a linear isometry. We already know that such a rotation is going to be a linear map. And of course, since we are rotating about the origin itself is fixed. If we were rotating the plane about some other point, well, then the origin would get moved, and it couldn't be linear. One more example. Any reflection is clearly going to be an isometry. When we start with a figure and we reflect it over a line, of course, the distances between points will be preserved. If I look at a certain distance in the original figure, it will be the exact same in the reflected image. So reflection is an isometry. And if I'm working in R2, and I particularly am concerned with reflection over a line through the origin, well, then the origin lies on the line of reflection, so it doesn't get moved. And we know that such a reflection is a linear map. So this would not merely be an isometry, but it would also be a linear isometry. It's an isometry that is also a linear map. And as we will see very soon, linear isometries have nice matrix representations. There are certain things that are true of the matrix representations of linear isometries that are not true of linear maps in general, but more on that shortly. Interestingly, we have almost exhausted all the types of isometries of a two-dimensional space. Translations, rotations, reflections. What else is there? Can you think of anything else? Well, really, the only other type of linear isometry in a two-dimensional space is something you can get by composing a reflection and a translation. For example, if instead of mapping our smiley face and R straight to its mirror image over here, if we had mapped it instead to this spot right here, so that the transformation combined a reflection and a translation. Such a thing is called a glide reflection. It's a perfectly good isometry, but it is not linear because the translation part ensures that it will move the origin. So we won't actually be concerned with such things here. And in fact, if you ever study these things in a geometry class, one thing you will surely prove, which is very interesting, is that every isometry of the plane, linear or not, can be decomposed into a sequence of reflections alone, so that reflections are like the atoms of isometries, or the prime numbers of isometries, if you want to think of them that way. For example, a rotation can be broken down into a sequence of reflections. You need two of them, in fact. Oh, I'll show you one example. Come with me over into the corner. Let's begin with our familiar winking face and the R, and rotate about the origin by 180 degrees. So we got from here to here through a rotation. But we could also have gone from here to here through a specific sequence of reflections. Namely, if we took our original stuff and first reflected it over the vertical axis, and then took that first reflected image and reflected it over the horizontal axis. And that composition of the two reflections is equivalent, in effect, to the single rotation. You can, in fact, do such a thing with any rotation about the origin or any translation. They can both be broken down into compositions of reflections. The proof is interesting, but this linear algebra class is not the place for such things. Look it up if you're interested. There is one more thing, though, I need to say about isometries in general before we start connecting it back to linear algebra. By definition, an isometry preserves distances, but it is a logical consequence of this definition that an isometry also preserves angles. We don't have to include that in the definition because it follows logically from the preservation of distances. The reason why this happens is very easy to explain, so I will do that quickly. First, purely intuitively, I think it's fairly obvious. There are no distortions in an isometry. And if you're not distorting anything, you're not changing any angles. But if we really wanted to nail this down with a geometric proof, we'd say, well, suppose I have an angle that I hit with an isometry. Does the angle get preserved? Well, let's see. The angle sits at a certain vertex, let's call it V, and we'll pick a point on each arm of the angle, let's call them A and B. And when we apply the isometry, all three of these points, V, A, and B, get mapped to new points. And who knows where they are? Maybe, for example, V gets mapped to this point. Let's call it V prime. But once I know where V gets mapped, that tells me a lot about where A can get mapped, because this distance between A and V has to be preserved by the isometry. So if I took that distance, measured it off from V prime, and made that the radius of a circle, I know that A prime, the image of A, has to lie somewhere on that circle. And something similar, of course, happens when we think about the image of B. But we don't need to worry about the details too much here. I know that some specific distance separates A and V, and some other specific distance separates V and B. And in fact, let me go ahead and draw the line from A to B, because some particular distance separates those points. Well, wherever A and B get mapped, all those distances have to be preserved. So we might end up with a picture something like this, or it could look slightly different, but all those three distances must be preserved. Now look at these two triangles. They are congruent triangles because all their corresponding sides are equal, right? That's the side, side, side criterion you probably learned in a geometry class long ago. That means all the corresponding angles must be equal as well. So this angle right here, angle AVB, is equal to the corresponding angle over here, angle A prime, V prime, B prime. And there it is. And that means that this angle we started with is preserved by the isometry. So the moral of the story is, by definition, isometries preserve distances, but an isometry preserves angles too. Good, I'll use that fact soon. All right, so I've introduced you to isometries. Our interest is specifically in linear isometries, and we will be particularly interested in their standard matrix representations. Their matrix representations relative to the standard basis. Let's think about what these would look like. So the next question we want to consider is, if A represents a linear isometry relative to the standard basis, what do its columns look like? This will have a very simple answer. We just have to think our way through it. The columns of A, our representation of an isometry, we know, of course, from chapter 3, are the images of the standard basis vectors under the isometry. So to be concrete, let's say we're working with a linear isometry defined on R3. So we might think about the standard basis for R3, I, J, and K, and then we hit the space with our linear isometry. Well, being a linear map, it moves these three standard basis vectors around, and the whole grid follows it. But being an isometry, there's only so much damage, so to speak, that it can do. For instance, wherever this yellow vector, let's say that's I hat, gets mapped, because this is an isometry, its image will still be unit length, because isometries preserve distances. So unit length in the domain means it's going to be unit length in the range. Now it could be pointing in any direction, but it has the same length that it had before. And of course, the same is true of the other two standard basis vectors. Their images will also have unit length. And since the images of these vectors are the columns of the isometry's matrix representation, then we have one piece of information about what those columns look like. The columns will be unit length. But that's not all. There is a second important fact about those columns. I said that I hat, for example, could have been mapped anywhere in R3 so long as it goes to a vector of unit length. So its tip could be anywhere on a sphere of unit radius centered at the origin. But once we know where it goes, the image of j hat is much more constrained, because not only must it be unit length, but it must also be perpendicular to the image of I hat, because isometries preserve angles. I told you I would use that in a moment, and the moment has now come. So now we have to think about the set of all vectors that are unit length and perpendicular to this vector. There are still infinitely many places it could lie, but now it can't be any one of those vectors whose tip is on that unit sphere. It would specifically have to be the ones that lie on a particular great circle of that sphere, the one whose plane is perpendicular to the image of I hat. So let's just say that j hat gets mapped to one of these vectors that is unit length and perpendicular to the image of I hat. Good. Well, now the possibilities for k hat's image are very limited, because not only must its image be unit length, since isometries preserve distances, but its image must also be perpendicular to the image of I hat and to the image of j hat, since k hat itself is perpendicular to I hat and j hat, and isometries preserve angles. That means there are actually only two places that k hat's image can go. One will look something like this, and the other will look something like this. I'll pick this one down here for the sake of our illustration. But no matter where it ended up, these three vectors, the images of the standard basis vectors, those will be the columns of our standard matrix representation of the isometry, and because of the preservation of angles, they, just like the vectors from whence they came, must be mutually perpendicular. So the columns of the matrix we are considering will be not merely unit length, but mutually perpendicular. And of course, even though I illustrated this with an example in R3, the same would hold in Rn more generally, because the standard basis vectors of Rn have unit length and are mutually perpendicular. And so if we apply an isometry which preserves both distances and angles, the images of the standard basis vectors, and therefore the columns of the isometry's matrix representation, will also have unit length and be mutually perpendicular. Good. Okay, so we see why this is so, but still it helps to think about some concrete examples, such as a rotation about the origin in R2 by an angle of theta. Well, we know explicitly what that matrix would look like. I hat, whose tip is at 1, 0, rotates through an angle of theta, and of course its new coordinates by basic trigonometry will be cosine theta, sine theta. And where does j hat go? Well, of course, the images of j hat and I hat will be, like j hat and I hat themselves, perpendicular to one another. And as we've discussed several times in this series of videos so far, to take a point and rotate it 90 degrees is easy to do in standard coordinates. You just swap their positions and negate the first one. Okay, so we know, of course, that this map is a linear isometry. We just would like to see these two facts about the columns that we deduced in a very general setting. We would like to verify that they hold here in a concrete example. Well, clearly they do. Are the columns unit length? Of course, this follows immediately from the way we compute the length of a vector given in standard coordinates. What's the length of this first column? It's going to be the square root of the sum of the squares of the components. But the sum of the squares of the components, cosine squared plus sine squared, is of course 1, and the square root of 1 is 1. So yes, that first column has unit length. Same story for the same reason with the second column. Good. Is it true that the columns are mutually perpendicular? Well, there's only two columns, so we just have to check, are they perpendicular to one another, which we can do very easily by thinking about their dot product. And we know from all the way back in chapter 1 that when we are working in the standard coordinate system, we can get the dot product of two vectors just by multiplying the corresponding components of the vectors and then adding up all the products. Well, here that would give us minus cosine sine plus cosine sine. So yes, the dot product of these two vectors is 0, and therefore these columns are perpendicular vectors, which of course we knew already. So this is just confirmation of what we knew before. And you would see the same thing if you wrote down the standard matrix representation for any isometry whose matrix you can easily compute. To take one more example, let's consider reflection in R3's xy plane. All right, what would the matrix representation of that map look like? I mean, it's a reflection, so it's an isometry, so we know it's going to satisfy these two conditions, but let's verify it. All right, well, what happens to I hat? When you reflect it in the xy plane, it doesn't move, so it stays as I hat. Same story with j hat. But k hat, when you reflect it in the xy plane, becomes the opposite of itself, which would make the third column 0, 0, minus 1. So here we have another example of a matrix representation of an isometry relative to the standard basis. Let's confirm that it satisfies these two conditions. Are the columns unit length? In this case, it's completely obvious because they are I hat, j hat, and minus k hat, which obviously are all unit length. And are they mutually perpendicular? Yes, of course they are. We can see that geometrically. It's this vector, and this vector, or by taking all the possible dot products of those columns, we would get 0 in every case. Good. So we have seen that the matrix representation of a linear isometry in standard coordinates will always have these nice properties of the columns, unit length and mutual perpendicularity. And it's also fairly obvious that conversely, any square matrix whose columns are unit length and mutually perpendicular must be the standard matrix representation of a linear isometry. As I said, this is fairly obvious because if we had such a square matrix, the fact that its columns are unit length and mutually perpendicular means that it represents a linear map that takes the standard basis onto something that looks just like the standard basis, where we have this frame that, like the original standard basis frame, generates a simple grid of cubes or squares or hypercubes or what have you, rather than the more generalized parallelograms or parallelepipeds or parallelotopes. And to get from the original to the new position, we can always carry that out either through some sort of rotation where we swivel this around and manage to get it into that position. That will work actually if the map preserves orientation, or if the map has reversed orientation, we might need to do a little swiveling and rotating, but then we might need to do some reflections as well to change the positions of the vectors relative to one another. But either way, we've got just some combination of rotations and or reflections that will get us from the original standard basis frame to the new basis frame, in which angles and lengths are the same as what they were before. And reflections and rotations are all isometries. So yes, if we have a square matrix whose columns are unit length mutually perpendicular vectors, so that we end up with a new basis frame that looks like the standard basis frame, then that matrix must be the standard matrix representation of some linear isometry. In a footnote in the book, I spell this out in a little more detail for those who might be interested. But as I said before, it's pretty obvious. So you should have an intuitive feel for why it is so. Okay, well, let's start to put all of this information together. If our square matrix represents an isometry, it has these two properties. And conversely, if we have a square matrix with these two properties, we've said it must represent a linear isometry. That is, if A is a square matrix, then A represents a linear isometry in standard coordinates if and only if A's columns are unit length and mutually perpendicular. So these are equivalent statements about square matrices. If we know our matrix represents an isometry, we know these two conditions hold. If we see a square matrix for which these two conditions hold, then we know it represents an isometry in standard coordinates. For example, if we see a matrix like this, a 3x3 matrix, a little quick calculation shows that its columns satisfy both of these conditions. For example, the third column here, if we compute its length, we're going to get the square root of 4/9 plus 1/9, 5/9, plus 4/9. That's 9/9, which is 1. So the square root is 1, and therefore the length of this column is 1. Same story with the other two columns. Moreover, some quick dot products show that any pair of columns here are perpendicular. For example, taking the dot product of the first two columns, we get minus 2/9 plus 4/9, that's 2/9, minus 2/9, that's 0. So these two columns are perpendicular. Same story with the other pairs of columns. That means that this 3x3 matrix definitely represents a linear isometry of R3. What sort of isometry? Well, we could explore that if we wished, but I don't wish. I just want to point out that it is so. Soon I will extend this list of equivalent statements, but first I need to introduce some terminology. And I will warn you up front that although I will initially present what looks like reasonable terminology, there's one little twist at the end, which is very unfortunate and unnecessarily confusing, but we're stuck with it because it's ingrained now. So let's start with some reasonable terminology. I'm going to begin by talking about some special properties that a basis might or might not have. An orthogonal basis is one whose vectors are mutually perpendicular. This is a pretty natural definition, at least if you know that orthogonal basically means perpendicular. I mean, I suppose we could have called this a perpendicular basis, but that would have been too easy, so we use a synonym. Actually, I will mutter down here in a low voice, there's a good reason for using orthogonal rather than perpendicular. When you do linear algebra in a more abstract setting, your vector spaces might not consist of vectors in the ordinary sense, and so the notion of perpendicularity is a little weird. For example, you can have settings where your vectors are actually functions. It's weird to talk about perpendicular functions. That doesn't make a whole lot of sense. So we use this more generalized term orthogonal. But shh, that's for more advanced stuff. For our purposes, orthogonal is just a synonym of perpendicular. All right, back to my regular voice. So given any basis, we can always ask, is it an orthogonal basis? Well, if the vectors are mutually perpendicular, it is. If they're not, it's not. So the standard basis in Rn is, of course, an example of an orthogonal basis, but it's not the only one. For example, these two vectors in my picture constitute an orthogonal basis of R2 because they are perpendicular to one another. Similarly, these three vectors constitute an orthogonal basis of R3 because any pair of them are perpendicular to one another. Okay, nothing deep here, and as I said, it's a natural enough definition. But all this talk of isometries and how it turns the standard basis into something that looks just like it might make you think, when I drew these pictures, gee, wouldn't it be nicer if these vectors were all unit length as well? Something more like these guys. Those look much nicer to work with. And indeed, they are much nicer to work with. So we have a special name for a basis of vectors that are not only mutually perpendicular, but also all unit length. To wit, an orthonormal basis is one whose vectors are mutually perpendicular and unit length. And this terminology is perfectly reasonable as well, because it's consistent with other ways in which we use the word normal. For example, all the way back in chapter 1, I introduced you to the idea of normalizing a vector, which was where you take a vector and divide out by its length, resulting in a vector pointing in the same direction, but guess what? Unit length. So we could turn any orthogonal basis into an orthonormal basis by normalizing all of its vectors. All right, so far, so simple. And many of you who are watching this are probably thinking, oh yeah, I can start to see how all this stuff connects up to what we were talking about here, because isometries take the standard basis and turn it into an orthonormal basis. And that is absolutely correct. But here is where the terminology is a little unfortunate. Namely, a square matrix whose columns are mutually perpendicular and unit length is called a orthogonal matrix. What? Orthogonal? Shouldn't it be called an orthonormal matrix? Well, yes, it should, but it isn't. Orthogonal it is. How did this strange state of affairs come to be? I truly do not know. But unfortunately, it's too late to change it now. It's awkward, but it's no great tragedy. And like the many thousands of others who have come before you and have learned linear algebra, you too will get used to it pretty quickly. So once again, we say that a basis is orthogonal if it consists of mutually perpendicular vectors, and if those mutually perpendicular basis vectors are also unit length, we call it an orthonormal basis. But if we have a square matrix whose columns are both mutually perpendicular and unit length, we just call it an orthogonal matrix. Fortunately, there is no such thing as an orthonormal matrix, so the potential for confusion is fairly limited. But anyway, with our definition of an orthogonal matrix locked down, we recognize that we've been talking about orthogonal matrices all along. So this stuff is true of matrix A if and only if A is an orthogonal matrix. It's just a cleaner way to say all of this stuff. Now, instead of saying over and over again, A is a square matrix whose columns are unit length and mutually perpendicular, we can just say A is an orthogonal matrix, which carries all that information. And so now we see that a square matrix is orthogonal if and only if it represents an isometry in standard coordinates. These are words that might not have meant anything to you before this lecture or before reading the corresponding section of the book, but now we see that they are intimately related. And I guess while we are at it, we might as well rewrite this statement in yet another form, which is that A's columns constitute an orthonormal basis for Rn. This is assuming our square matrix is specifically an n by n matrix. So a 3 by 3 matrix is the standard representation of an isometry in R3 if and only if its columns constitute an orthonormal basis for R3, which is another way of saying that A is an orthogonal matrix, meaning that its columns are unit length and mutually perpendicular. So lots of different ways of saying the same thing, many of them involving new terminology. But once you get it down, this is the kind of thing, again, you should just be able to think about and see very easily. It makes perfect sense once you understand what an isometry is, what an orthogonal matrix is, what an orthonormal basis is, and you can think about these things geometrically. But you know what? There's a very good question you might ask here. Who cares about any of this stuff? We've introduced a lot of terminology and ideas and seen the ways that they are stitched together. We've seen a bunch of equivalent statements about a square matrix A. It's the standard representation of an isometry, or it's an orthogonal matrix, meaning that its columns are unit length and they are mutually perpendicular, or its columns constitute an orthonormal basis. And all of these statements stand or fall together. When we have a square matrix, it either satisfies all of them or it satisfies none of them, and there's no in between. But still, why should we care about all this stuff? Well, I will give you 3 main reasons why we should care about all things orthogonal and orthonormal. First, orthonormal bases are the easiest ones to visualize. After all, any orthonormal basis gives us a frame that looks just like the frame for the standard basis vectors, except it's just been rotated a bit or reflected or something like that, subjected to a simple rigid motion, an isometry. So the grids that these things determine are familiar grids of squares or cubes or hypercubes in higher dimensions. And we don't have to think about the distortions that come with parallelograms or parallelepipeds or parallelotopes. So orthonormal bases are convenient in part just because they're comfortable. They're what we know. They're what we grew up with. So this is a small reason why we might care about this stuff, but it shouldn't be underestimated. The second reason we should care is really the primary one. When we use an orthonormal basis, the familiar formulas for the dot product of 2 vectors and the length of any individual vector, the formulas we learned back in chapter 1, still work. And this may not seem like such a huge thing, but when we have easy access to the means of computing lengths and the dot product, which gives us angles, then we can start to measure all sorts of things in natural ways. Areas, which are products of lengths, and volumes, which are products of 3 lengths, and hypervolumes, and so on and so forth. So the whole world of measurement really opens up to us in a very simple and familiar way. It's all familiar from working with the standard basis, but these things don't work if we're working with just an arbitrary basis. We'll talk about that in a moment, because this requires a great deal of explanation, but I want to go ahead and mention the third reason why we should care about this general cluster of ideas. Number 3 is not as far-reaching as number 2, but it's very nice indeed. It is that orthogonal matrices are very easy to invert. And that's nice because if you think back to chapter 4, where you learned the inversion algorithm, inversion is normally a real pain. It's not a pain at all when you're dealing with orthogonal matrices. More on that in a few minutes as well. Numbers 2 and 3 both require careful explanation. So let's start with 2, and because I might need some more room here, let me shrink all that red stuff down to a tiny size, and if need be, I will expand it back out later. But we want to talk about those formulas for dot product and length. Let's begin with the dot product. I have to review something very quickly because this is from a long time ago, way back in chapter 1. Recall from that chapter that when we defined the dot product of two vectors, we did not do it in terms of the coordinates of those vectors. And I made a big deal out of this throughout the whole chapter, that for as long as possible, we were going to work coordinate free. And the way we defined the dot product was as the product of the scalar projections of both vectors onto either one of the vectors. So for example, the dot product of these two vectors, v and w, would be the product of this green length, v's scalar projection onto w, and this purple length, w's scalar projection onto itself, which is of course just its own length. And that's how we defined the dot product. v dot w is the product of those two scalar projections. This definition makes no mention of coordinates of these two vectors, just thinking of the vectors as geometric objects. And we used this geometric definition to derive almost all of the basic properties of dot products in a coordinate-free manner. For example, we proved the familiar property that when you dot a vector with itself, you get the square of its own length. And we don't need anything about components to see why that's true. We just think about the geometric definition. Because if we have v dotted with v, we're looking at v's scalar projection onto itself, which of course is its own length, and, well, v's scalar projection onto itself, which is again its own length. The dot product is the product of those two scalar projections, so it's the length of v times the length of v, which is of course the square of the length of v. And we proved many properties of the dot product purely geometrically without using coordinates at all. For example, we proved that the dot can be distributed over vector addition, and we proved that when doing dot products of vectors that have been scaled, we can pull the scalars out front and just consider the dot product of the vectors themselves without those scaling factors. We proved that two vectors are perpendicular if and only if their dot product is 0, which again is totally obvious from the geometric definition of the dot product as a product of scalar projections. After all, if we have perpendicular vectors, what's their dot product? Well, it's the product of the scalar projections of the two vectors onto one of them. So let's say we project onto w, but what's the scalar projection of v onto w? It's 0 because it doesn't cast any shadow because the vectors are perpendicular. So it would get 0 times the length of w, which would therefore be 0. That would be the dot product of any two perpendicular vectors. Again, no mention of coordinates anywhere. And as I say, we proved lots of properties like this. You can revisit all that in chapter 1 if you want to. But there was one formula connected with the dot product that specifically refers to the coordinates of the two vectors. And you know the one I'm talking about. It says that if we have v's components and w's components, then the dot product of those vectors is computed in the familiar way. We take the products of all the corresponding components and then add all those products up. Now, this famous formula for the dot product has a different status than those other properties of the dot product that I wrote down a moment ago. It has a different status because this is the only one that refers to the components, the coordinates of the vectors. And back in chapter 1, way back when we were young and foolish, and we hadn't even met the notion of a basis yet, which came in chapter 2, we just thought of these things as the coordinates of the vector. But now we are older and wiser, and we are at the end of a chapter all about change of basis and coordinates. And now when we look back on this thing, we think, hey, wait a second, in a different basis system, v and w would have totally different coordinates. Will this formula still work? And the answer is only sometimes. We know it works in the standard basis system because that was the only one we knew when we came up with these things in the first place. And in fact, if we were looking back on chapter 1 from our more sophisticated standpoint now, the way we would really write this formula is to say something like, not if v is equal to that thing, because after all, now we would say, well, v is a geometric object and this thing is a stack of numbers. They're related, but maybe equals is pushing it a little too far. what we should really say is if V's standard coordinates, its coordinates in the standard basis system, are V1, V2 all the way down to Vn, and same thing over here, not W, but if W's coordinates relative to the standard basis are these things, then this formula holds. What we're really asking is, if we were to change the basis and not use the standard basis system, but write V and W's coordinates relative to some other basis, would this still hold? And as I've said, the answer is only sometimes. There was an exercise about this earlier in the chapter, in fact, but in case you didn't do that exercise, naughty, naughty, I will remind you of the punchline. Here's a picture in R2, and these two vectors B1 and B2 obviously constitute a non-standard basis B. And these things correspond to one side and the diagonal of a square. And for the sake of argument, let's just say that this is the unit square, so that the length of each side is 1 unit. Okay, in that case, what is the dot product of those two vectors? Well, we know how the dot product is defined, which is through geometry. We're not going to use any weird formulas having to do with coordinates because we're not sure if it works there, since we're not using the standard basis. But we do know how to find this. That dot product is the product of the scalar projections of the two vectors onto either one of those vectors. Let's project onto B1. Well, the scalar projection of B2 onto B1 is, of course, just the length of the edge. That's the shadow this thing casts there. So that's 1 unit. And the scalar projection of B1 onto B1 is, of course, its own length, which is 1 unit. So the dot product of those two vectors is 1. But could we have computed that by writing down the B coordinates of these two vectors and doing that usual arithmetic operation? Well, let's see. The coordinates of B1 relative to basis B are what? Well, let's see. To get here, we take one B1 step and no B2 steps, so we would get 1, 0. And by the same logic, the B coordinates of B2 are obviously 0, 1. So if I tried to use that coordinate matching formula, I would get 1 times 0, which is 0, plus 0 times 1, which is 0. So when I multiply corresponding components and add them up, I would get 0, which is not the dot product, which we know is 1. Oi! That means that our beloved formula does not work for arbitrary bases. Such a tragedy. So we have to be careful, and for the moment, just hunker down and say, all right, we know this formula works when we represent our vectors relative to the standard basis. I mean, even in this case, we could do that and everything would be fine, because if we had represented B1 relative to the standard basis, well, this is 1 unit here. Obviously, this point would be 1, 0 in standard coordinates, but when we represent B2 relative to the standard basis, we get something very different, because that point is 1, 1 relative to the standard coordinates. And now, since everything is in terms of standard coordinates, yes, we can play our old game, just like we proved back in chapter 1, and we would get 1 times 1 is 1, plus 0 times 1 is 0. So yes, that little recipe would give us 1, which is indeed the correct dot product. So all praise to the standard basis. And recognizing this sort of thing puts a damper on our enthusiasm, at least a little bit, for non-standard bases. But, if we're working with an orthonormal basis, then all is well and the formula will still hold even when we write our coordinates in terms of that other orthonormal basis. And I will prove why that is so. So to set the stage, let's let crazy B be an orthonormal basis, whose vectors we will call B1 through Bn. And let's let V and W be two vectors in the space for which B is a basis, and we want them so that V's B coordinates are C1, C2 all the way down to Cn, and W's B coordinates are D1, D2 all the way down to Dn. And I claim that the dot product of V and W will be, thanks to this beautiful orthonormal basis, C1, D1 plus C2, D2 plus all the way down to Cn, Dn, so that we can actually play that game where we just multiply the corresponding coordinates and then add them all up. And if our basis is orthonormal, it really will give us the dot product. Why is that so? Is this some mystery that we can't understand? No, we can understand it. Here's the proof, which is basically the same proof we used to prove this formula back in chapter 1, but maybe you'll appreciate it a little more now. And I may need some room, so let me get rid of that stuff. All right, V.W. I'm going to rewrite those two vectors in terms of their components. So V is going to be C1, B1 plus C2, B2 plus all the way to Cn Bn. That's what it means, after all, for that stack of C's to be the B coordinates of V. And similarly, W can be expanded out as D1 B1 plus D2 B2 plus all the way to Dn Bn. And now, remember how I said that in chapter 1 we proved all of those many properties of the dot product that did not depend on coordinates in any way? Well, we're going to use those properties to rewrite this in a much nicer form. One thing we said was that the dot product distributes over vector addition. So I can take this whole thing and say it's this dotted with the first term, plus this whole thing dotted with the second term, plus this whole thing dotted with all the way down. And in each one of those terms, like the first one where I'd have all this stuff dotted with just the first term, then I will distribute this guy, the first term, through these vector additions. So I would get this first term dotted with this first term, and this first term dotted with the second term, and this first term dotted with the third term, and so on and so forth. And if you go through all of those many distributions, which I'm not going to write out, of course, you would end up with it working exactly as it does in elementary algebra, where to multiply, here take the dot product of these two things, we have to take every term in the first group and dot it with every term in the second group. So after all that distribution, which we know we can do without any reference to coordinates, we could rewrite all that stuff as something like this. Bunch of terms, where the first one is the dot product of the first term in the left group and the first term in the right group. And then we have this next term, which is the first term from the first group, and the second term from the right group. And on it goes until we get all the different combinations, culminating in the last term from the left group and the last term from the right group. Good. And just as we were able to prove that the dot product distributes over vector addition in a coordinate-free manner, we proved that we could pull scalar multiples through a dot product. And if we do that in every term here, we can rewrite this stuff as all this stuff. And that property of being able to pull scalar multiples through the dot is one of the other properties we proved without any reference to coordinates. And now we're close. So far, we haven't used anything specifically related to the fact that our basis is orthonormal. That is about to change because we have all these different terms. In some of them, like say this second one, the dot product that we've isolated is between two different vectors in our basis, v1 and v2. Well, it's an orthonormal basis. We know that in an orthonormal basis, the basis vectors are mutually perpendicular, which means v1 and v2 are perpendicular, which means that their dot product is 0. So that term gets wiped out. And not just that term. Most of the terms in here get wiped out. All the ones where the two basis vectors we are dotting are distinct. The only ones that survive are ones like this one and this one, where we're dotting a vector with itself. But when we dot a vector with itself, that, as we said, was another property we proved without any reference to coordinates. Dotting a vector with itself gives us the square of the length of the vector. But what's the length of B1? Well, it's a vector from an orthonormal basis. These all have unit length. So the square of that unit length is, of course, just 1. So that becomes a 1, and that becomes a 1. And all the way down, we get 1s for any term where we had B1.B1, or somewhere down here we'll have B2.B2 and B3.B3, and all the way to Bn.Bn. Those are all 1s, and those are the only things that survive. So when all the dust settles, we get C1D1 times 1, which I'm not going to write, a bunch of zeros, and then we have a C2D2, and on we go, until at the end we get CNDN. And so there, at long last, is everybody's favorite formula for the dot product. It doesn't work for arbitrary bases, but it does still work when we have an orthonormal basis. Hallelujah. So now we see that thing we proved, that formula we proved back in chapter 1, sure, it held for the standard normal basis, but it held there because the standard normal basis was an example of an orthonormal basis. It holds for any orthonormal basis. Excellent. In fact, come to think of it, let's put this to the test with that picture I drew a minute ago. Here were our two vectors, b1 and b2. We know that b1.b2 is 1 because the product of those two projections is 1. Suppose we tried to compute it using that formula, but using an orthonormal basis that is not the standard basis. Let me move this up a little bit, and let's use these guys as our orthonormal basis, which I will call basis crazy A. Well, let's write B1 and B2 in A coordinates. What are those going to be? Well, B1's A coordinates, to get to B1, the end of B1, we take one negative A2 step. So its coordinates will be 0, -1. As for B2's A coordinates, let's see, to get there, we could take a negative A1 step and a negative A2 step. So the A coordinates for B2 would be -1 and -1. Well, let's see what happens if we do everyone's favorite arithmetic operation on the coordinates of these vectors. We get 0 times -1 is 0, plus -1 times -1 is, it's 1. So yes, indeed, just as we proved, we can still take the dot product of these two vectors by using that component matching formula, even when our coordinates are expressed in some other orthonormal basis. The orthonormality is essential here. Excellent. I think the point has been well made, and now it is time to explain why the formula for the length of a vector still works under these circumstances as well. So let me remind you of what we are trying to do. All the way back in chapter 1, we proved that if the standard coordinates of a vector v are v1 through vn, then v's length is given by a very simple formula in terms of those coordinates. It's the square root of the sum of the squares of the coordinates. And once again, back in chapter 1, we didn't write it quite this way. We didn't talk about the standard coordinates of v. We just wrote if v is equal to this thing, because this wouldn't have meant anything to us then. We were only working with the standard basis. But now that we recognize that the standard basis is just one of many, we would like to ask the question, does this basic formula hold even if we used a different basis to get our coordinates? I mean, if instead of the standard basis I use some other basis, then the vector's coordinates will all change. And the question is, if I square them all and then sum those squares and then finally take a square root, do I actually get the vector's length? And the answer, as we've said a few times here, is yes, if the new basis is orthonormal. If it's not orthonormal, then probably not. And before we prove that this is so, let's just do a few concrete calculations to gather some evidence, as it were. So let's look at this same picture again. We really have three bases written here. Basis A, consisting of these two vectors, basis B, consisting of these two vectors, and the standard basis, consisting of, well, I and j. Now, since B2 lies along the diagonal of a unit square, we know that its length is the square root of 2. But let's write B2's coordinates in each of the three bases we have here. With respect to the standard basis, its coordinates are 1, 1. With respect to basis A, B2's coordinates are -1, -1. And with respect to basis B, B2's coordinates, of course, are 0, 1. Now, if we were to try applying that formula, the square root of the sum of the squares of the components, in each of these three cases, let's see what would happen. Well, in the first case, the standard basis, we'd get the square root of 1 plus 1, so the square root of 2, which is correct. Well, we knew that already. But much more interestingly, if we apply that formula in this case, where we're using basis A, which is another orthonormal basis, we get the square root of 1 plus 1. So again, we get the square root of 2, which is correct, just as I said it would be. But if we try it in the third case, where we're using basis B for our coordinates, basis B is not orthonormal, and applying that formula gives us the square root of 0 plus 1, the square root of 1, which is 1, which gives us the wrong value for the length. So that length formula does not work in the case of this non-orthonormal basis. Okay, so that's evidence that what I'm telling you is true, but we are looking for proof. Our claim is that if crazy A is an orthonormal basis consisting of vectors A1, A2, all the way to AN, and V is some vector whose A coordinates are C1, C2, all the way down to Cn, then V's length is indeed given by the square root of the sum of the squares of those coordinates of V relative to the orthonormal basis. And the proof is so short, thanks to the work we've done already, that I can fit it in this tiny space. We know something about the square of the length of any vector. We proved in a coordinate-free manner back in chapter 1 that the squared length of any vector is always the dot product of that vector with itself. But of course, what we're really interested in is just the length itself. So let's take the square root of both sides of that to obtain this equation. Now, I still want to do something with v dot v. What can I say about that? Well, I can say quite a lot because I know v's coordinates relative to an orthonormal basis. As we proved just moments ago, when we have vectors' coordinates relative to an orthonormal basis, we can take those vectors' dot product using everyone's favorite dot product formula, multiplying the corresponding components and adding up the results. So when I do that here, the two vectors are identical. So I get c1 times c1, that's c1 squared, plus c2 squared, plus c3 squared, all the way down to plus cn squared. So this stuff becomes precisely what we said it was going to be. Good. And now it's time to bring back our little shrunken outline to remind us what we are doing. We were explaining why we should care about this cluster of ideas involving orthogonal matrices, orthonormal bases, isometries, and the rest. We said that orthonormal bases are easy to visualize. Good. We said that when we have an orthonormal basis, the familiar formulas for dot product and length still work. Good. And now we need to look at number 3, which is about orthogonal matrices. I claimed that they are very easy to invert. Recall what a pain it was using the inversion algorithm. Given some invertible matrix A, we had to form an augmented matrix with it on the left and the identity matrix on the right, and then we had to boil it all the way down to reduced row echelon form, which would leave us with the identity matrix on the left and then something on the right. And that something turns out to be the inverse matrix of the original matrix A. Well, it's a nice little algorithm, but it's very expensive computationally, especially if A is a large matrix. However, I claim that if Q is an orthogonal matrix, meaning that its columns are unit length and mutually perpendicular, then Q inverse not only exists, but is also equal to, of all things, Q transpose. Ooh, the transpose. We've made mention of it a few times, but here's the first time it's making its appearance in a legitimately interesting way. A few comments before we get to the proof. First of all, you might have looked at this statement and said, Q? What perversity is this? Why not just use an ordinary letter like A or M? Well, Q is the traditional letter used for known orthogonal matrices. For example, in a Chapter 8 exercise, you will run into something called the QR factorization of a matrix. And in such a factorization, the Q specifically stands for an orthogonal matrix. So if you've seen Q used in this way before, when you encounter something like QR factorization, you won't be surprised as to the meaning. But there's nothing special about it. We could have called this A or M if you really wanted to, but I'll go ahead and get you used to Q. The second thing I want to mention about this before we prove it is that if this is true, it is, then instead of that gory inversion algorithm, inverting an orthogonal matrix would become trivially simple. What could be easier than taking the transpose of a matrix? Not much. So we would be swapping a tedious, computationally expensive algorithm for utter triviality. All right, let's explain why this is true. So we've got an orthogonal matrix. We want to prove that its inverse is its transpose. Oh, first of all, how do we know it's even invertible? I should have asked that. If you have taken to heart these equivalent statements about a square matrix, then you might see two different ways to see why any orthogonal matrix has to be invertible. The easiest is to recognize that an orthogonal matrix represents an isometry, and obviously isometries can be undone. They don't crush any dimensions or anything like that. They don't distort space at all. So they're definitely invertible. So by pure geometric reasoning, it's obvious that orthogonal matrices are invertible if we understand that they represent isometries, because isometries are obviously invertible. Another way we could have seen that it's invertible would have been to recognize that to say that a matrix is orthogonal is equivalent to saying that its columns constitute an orthonormal basis for the appropriate space. We don't even need the orthonormality. The fact that the columns constitute a basis is enough to tell us by that old invertible matrix theorem that the matrix must be invertible. Okay, so anyway, if Q is an orthogonal matrix, it's definitely invertible. But why is its inverse its transpose? That's the claim. Well, the way we're going to prove this, we're going to sneak up on it. To say that the inverse of Q is Q transpose is to say that if I multiply Q transpose and Q, I get the same thing as if I multiplied Q inverse and Q. Namely, I would get the identity matrix. So to prove our claim, I am going to prove just that the product of Q transpose and Q is the identity matrix. Now, how are we going to prove that? Well, what we're going to do is figure out what the ijth entry of this matrix product is. In other words, for any I and j, what's the entry in row I, column j? That's going to help us because we know exactly what that is like in the identity matrix. The entries are all ones if they're on the main diagonal, or all zeros if they're not on the main diagonal. So let's get to work. We've got our product, QTQ. What can we say about its ijth entry? Well, quite a lot, because we know the entry perspective on matrix multiplication. When we multiply two matrices, the ijth entry, as we learned all the way back in chapter 3, is a certain dot product, namely the ith row of the first matrix dotted with the jth column of the second matrix. Okay, fair enough. We know this equal sign holds by the entry perspective on matrix multiplication. Oh, but look, we're talking about the ith row of the transpose of Q. Well, think about the meaning of the transpose. The transpose swaps the rows and columns. So instead of saying the ith row of Q transpose, we could say, well, that's the same thing as the ith column of Q itself. And we are dotting that with the jth column of Q itself. Oh, that's interesting, because now we're taking the dot product of two columns of Q, our orthogonal matrix. And we know quite a lot about the columns of an orthogonal matrix. So let's put that knowledge to use. If I and j are distinct, like if we're talking about the second column and the eighth column, then we know what their dot product is, because we know the columns of an orthogonal matrix are all perpendicular to one another, and perpendicular vectors have a dot product of 0. Oh, so that means I already know that this dot product is 0 in the cases where I and j are distinct. But what about the cases when I and j are equal? Like maybe we're not talking about the entry in row 2, column 8 of this product, but the entry in row 5, column 5. Well, that would be the dot product of Q's fifth column with Q's fifth column. So we would be dotting one of Q's columns with itself. And we know, as we've said many, many times now, that when you dot a vector with itself, you get the square of the vector's length. But we know what the length is of all the columns in an orthogonal matrix. In such a matrix, the columns are unit length, and you square 1, and of course you get 1. So let's see what we have found. We've got an orthogonal matrix, and we've just shown that if you multiply its transpose by that matrix, then the entries are all zeros and ones. That's looking promising. And in fact, they're all zeros, except you get ones in the ijth entry when I and j are equal. So entry 1, 1, the top left corner, is going to be a 1. Entry 2, 2, row 2, column 2, is going to be a 1. Entry 3, 3, row 3, column 3, is going to be a 1. And all the way down. Well, those are just the entries on the main diagonal, and everywhere else we get zeros. So it follows that the matrix that is produced when we look at Q transpose Q is nothing other than the identity matrix. Hence, Q inverse, the matrix we have to multiply Q by to get the identity matrix, is nothing other than Q transpose as claimed. Let's consider a quick example. Let's let Q be this 3x3 matrix, which we actually saw earlier in this video. Now, Q is orthogonal, which you could see if you took the time to verify that each of its columns are unit length and that any pair of them are perpendicular. So it follows that Q is invertible, so it makes sense to write this symbol down, and moreover, its inverse is its transpose, because that is a nice property of orthogonal matrices. And it would be fairly unpleasant to invert this thing with the inversion algorithm, but if all I have to do is write down its transpose, well, that just takes a second. So it's a very nice property. I should mention two last things about it. First of all, we proved that if Q is orthogonal, then its inverse is its transpose. The converse is also true. You can prove that if you have a matrix whose inverse is its transpose, then that matrix must be orthogonal. The proof is basically the same proof we used to show that orthogonality implies that inversion is the same as transposition. You just have to run the steps backwards. I'm not going to go through the details. But if we take that as read, then we see that we can go back and forth between these two properties, orthogonality and inversion being the same as transposition. Oh, wait, that means that I have a fourth statement to add to this list of equivalent statements. A inverse is A transpose. If that holds, then all the rest follows. And if any of them hold, then that follows. Again, these all stand or fall together. And the last thing I will mention is that it's really nice having a matrix whose inverse is its transpose, not just because it's easy to compute, but because when we're changing bases, well, you remember how that worked. We would start with some matrix, and then we have to hit it on both sides with some matrix and its inverse. So the problem of inversion naturally comes up there. Well, if we are so lucky as to have a change of basis matrix that is orthogonal, well, then that piece of computing the matrix of the underlying map relative to the new basis is really easy, because once we have this, then inversion is really just a matter of transposition. Moreover, that would mean that our change of basis matrix, being orthogonal, is itself really just an isometry. And then we could understand this whole process as a matter of applying an isometry to the standard basis frame, rotating it a bit or reflecting it, getting it in a position where it was easy to understand what was going on, and then rotating back or reflecting back or getting back by means of some other isometry. At any rate, I may have more to say about that a little further down the road, but we have done enough for now. And we find ourselves once again at the end of a video, and in fact, the end of a chapter. In the next video, we will begin at chapter 7, where you will be initiated into the mysteries of the prefix eigen. So stay tuned for eigenvectors, eigenvalues, eigenbases, eigenspaces, and, well, you'll see. But for now, study this stuff well, do the rest of the exercises in chapter 6, and I will see you next time. Goodbye.